Okay, welcome back. So we left off talking about two terms that we can use to describe heat. The first type of heat is sensible heat that we identified as something we can measure, and the second one is a latent heat. And this is a type of heat energy that's stored within bonds, and it cannot be measured, but it can be observed. Now, when we talk about absorption radiation, we know that the Earth stores energy with the surface, on the surface, or it stores energy based on what the surface is made out of. So when we talked about albedo, surface is going to be huge because it's going to really determine how much energy gets reflected back out or how much energy is going to be stored. So we know that the absorption energy, that when it's absorbed by the Earth's surface, it's stored in on the surface in the form of dirt, in the form of grass, in the form of water. Okay, and this is energy that we can feel. We can feel a hot surface, and so this is referred to as the sensible heat. So the Earth's surface stores this energy, and it can release it at a later time. So it releases that energy by the surface. So we know that the sun's energy comes in to the Earth and warms up the Earth's surface. And as the Earth's surface warms up, it starts to warm up the air. Okay, so it allows for the air to become warmer. It allows for radiation to be re-radiated back out to space. We see conduction. We see the three different ways that heat can be transformed. We see radiation to the atmosphere or to space. We see conductions to the atmosphere. And we start to see evaporation and latent heat to the atmosphere, which we'll talk about later. Okay, so this is just the three different ways that heat can be stored as an example when we're talking about absorption radiation. Now, when we talk about evaporation, okay, remember we identified that latent heat is the energy that's stored within the bonds. And that when we talk about evaporation, we know that there's a large amount of heat that is going into boiling our water. Okay, so our water is now heating up. That energy is going into the water. That water is boiling and it's changing from liquid to a gas. So it's changing from liquid water to water vapor gas. And so when we're talking about latent heat, that latent heat is absorbed, okay, into the water and it's heated up. That energy breaks the molecules that is our water, and we cannot feel the latent heat or measure it, but we can see it when we start to see the water vapor when the water is boiling. Okay, so we know that latent heat is released when condensation occurs. Okay, it allows for the water to cool down and we start to see water droplets form as a result. So we're going to be talking about evaporation quite a bit and latent heat, especially when we start talking about phase changes and when we start talking about extreme weather. So just keep that in mind. Now, when we start talking about thermal properties of water, we know that water absorbs and releases latent heat. Okay, so remember that this is that energy that's stored in the molecular bonds. Now, remember that latent heat energy is stored in the bonds of the molecules. Okay, and again, I'm repeating myself and I'm reading the words on the screen, but this is something that is a fairly easy concept to say in your mind, but it's a complicated concept to understand. So when heat is absorbed by our hydrogen bonds, they start to loosen up, okay, or become broken. And when this happens, we start to see changes that take place in the water. So either ice starts to melt or water starts to evaporate, okay, because we have more latent heat being absorbed into the hydrogen bonds. Okay, so when latent heat is released, the hydrogen bonds are strengthened again. And so we see this, so energy is released. We see this, and we now have our water that is releasing energy and cooling down, and now it's being able to freeze. Or we see this when the air temperature drops and we have our water vapor in the air that we can't see water vapor, temperature starts to drop and we have condensation occur. Okay, so where it cools down, we start to have water vapor condense and it changes into liquid water droplets. So why are the thermal properties of water so important? Well, we know that the water is going to influence major weather patterns on Earth. Okay, it's going to have a huge influence. It has a huge influence on the weather that we experience here in Northern California, and water is going to be a huge driver of the atmosphere. Okay, so 30% of the energy required to drive the atmosphere is part of this process of water. Okay, so it helps regulate climate, which is going to be a huge element when we start talking about climate patterns. So an example of regulating climate would be, living on the coast. I lived in Arcata for 6 years, and the temperature fluctuation was only about 8 degrees. So 8 degrees from its highest temperature and 8 degrees from its lowest temperature. So it was very regulated. And it was regulated because we lived right on the coast. And the ocean absorbs energy and it releases that energy. And so it regulated the temperature so that we would only experience an 8-degree fluctuation. And as a result of that, one of the most important characteristics of water is that it absorbs and releases this energy. Okay, so that's why it's very important. Now, when we start talking about the global radiation budget, okay, so this is kind of complicated, but this is going to relate to the activity that you guys are going to be doing this week. You're going to be calculating the total amount of shortwave energy coming in from the sun, and you're going to be following that shortwave energy as it makes its way through clouds, and as a result, it's going to be reflected back out to space. Some of that energy is absorbed by the clouds. Some of that energy is re-radiated down to Earth as indirect radiation. And so you're going to be able to calculate the total shortwave energy absorbed by the Earth, okay, versus the total longwave energy lost by the Earth out to space, okay? And this will start to make sense as you start putting numbers in and following this whole budget. Now, when we talk about the global radiation budget, now this budget is a balance between incoming and outgoing radiation on Earth. Okay, so some places are going to be having more incoming and some places are going to be having more outgoing. Okay, and this budget allows for the Earth to function. Now, when we talk about this net radiation, it's the net difference between the incoming and outgoing radiation. Okay. Now, when you're talking about a budget of anything, so for example, a global radiation budget, you're going to see areas where you have surplus of energy. Okay, and notice that for this mean annual net radiation map, we have the equator right here. Okay, if you look a little closer, we start to see the continents. Here's South America, here's the continent of Africa, okay, here's North America. And so we are able to identify areas that have a surplus of energy. Now note the legend over here, the colors that we're looking at here is watts per meter squared. Okay, so it's a measurement of energy. Okay, so where would you expect to find a surplus of energy? Now the surplus are going to be the warmer temperatures or warmer colors. We see the yellows and oranges and reds. Now, hopefully your eyes are being drawn to this area right here. Okay. Now, remember that between here and here, this is the range of our subsolar point. So that's the area where we see that we have this surplus of energy. Okay? And that makes sense because that's the range and where the sun is its highest latitude, subsolar point's its highest extent in the northern hemisphere and then in the southern hemisphere. So it makes sense that there's this surplus of energy due to the subsolar point. Now, where we have a deficit at the poles. Okay, remember above the Arctic Circle and Antarctic Circle, we have 6 months of light and 6 months of dark. Okay, and so this is where we're going to experience a deficit. And when we talk about the budget as a whole, we talk about this balance, right, where we have a surplus versus deficit. And this deficit and surplus links back to where our subsolar point is at. So we can go ahead and look at different seasonal variations of our net radiation. So the first map that we're looking at is January. Okay, so mean net radiation. Now January, here we are, January. So where is the subsolar point in January? Now hopefully you guys are looking down at those warmer colors, right? So the subsolar point is down at 23.5 degrees, 23.5 degrees south, okay, so southern hemisphere. So it would make sense that there would be a surplus of energy in the southern hemisphere in January because it's northern hemisphere's winter. Now notice that we have a deficit here because we don't have the sun's energy. We don't have those long days that we have in the summer. Now let's go ahead and look at July, the mean net radiation for July. Now our subsolar point at highest extent is on June 21st, my wedding anniversary, and it's at 23.5 degrees north on June 21st. Now notice we see a surplus of energy in the northern hemisphere at this time and a deficit in the southern hemisphere. Now also I would love for you to look at the patterns of the oceans. Okay, so let's go back and look at the January map and see where, notice that you have a surplus of energy in these ocean basins. Okay, and we also see the surplus of energy here in the ocean versus the land. Okay, that's going to have a huge influence when it comes to talking about how land heats up versus how water heats up. Okay, so when talking about global radiation, you know that we don't have an equal amount of energy on the Earth's surface. We know we have areas where there's more heat, okay, due to the sun's subsolar point. And we know we have areas of deficit where we have 6 months of darkness and 6 months of light. So a question that I have for you guys is, which of the following is going to have the highest albedo? Okay, so our options are asphalt, grass, water, or snow. Okay, so highest albedo. Albedo meaning that it's going to reflect back the highest percentage. Now remember, out of these 4 categories, which one had the highest? Hopefully you guys are looking at, well, it can't be asphalt because that had a low albedo, which absorbed energy. Grass had a range of 5 to 15. Water, remember, it had a range from about 5 to 65%. And snow was the highest, had the highest albedo. So the answer for this question is going to be snow. Okay, so we're going to go ahead and move into talking about the Earth's atmosphere. Now, when we talk about the atmosphere, I want you to think of it as a layer of material, okay? Gases, clouds, a medium that our solar energy has to pass through, okay? Now, it's unique in our solar system. We have oxygen and carbon dioxide that allows for us to breathe, okay? That changes carbon dioxide into oxygen through photosynthesis. When we talk about the Earth's atmosphere, think of it as layers and layers and layers upon filters that allow for us, shields us from harmful shortwave radiation, so UV radiation. But when we talk about atmosphere, we can't talk about it as it being a static feature. The atmosphere moves, and it's very fluvial, meaning that it moves like ocean currents, it moves like eddies. So it has this liquid type quality to it. And there are 3 basic components of the atmosphere. There's constant gases, variable gases, and particulates. Okay, so when thinking about the atmosphere, I want you to think of layers upon layers upon layers of filters. Okay, and each of these filters are going to have different composition depending on which layer they're talking about. We know that the atmosphere protects us from harmful rays from the sun, and that there are 3 components: constant gases, variable gases, and particulates. So I'm going to go ahead and stop lecture here, and we'll pick up on the Earth's atmosphere for the next lecture.